At this very moment, somewhere among the stars scattered across our galactic neighborhood, there might be eyes looking up at their own night sky, wondering the same question we ask ourselves. Are we alone? Those beings, if they exist, might have cities that dwarf our own. They might have technologies that would appear to us as pure magic. They might even possess the knowledge needed to cross the void between stars. But here is the truth that nobody wants to acknowledge. None of it matters. The universe has constructed a prison so absolute, so fundamentally unbreakable, that no amount of intelligence, no degree of technological sophistication can ever set them free. This prison is not built from walls of ignorance or chains of primitive understanding. It is built from the bedrock of physical law itself, from distance that staggers comprehension, from energy requirements that beggar belief, from time that erodes all purpose. The question is not whether intelligent life exists elsewhere in the cosmos. The question is why the fundamental architecture of reality makes it effectively impossible for any of them to ever stand on Earth's surface. The barrier is not what they know. The barrier is what the universe is. If you want to understand the single most powerful argument against alien visitation, the argument that requires no speculation about probabilities or Drake equations or Fermi paradoxes, hit that subscribe button now. Make yourself comfortable. We are about to explore why the cosmos itself is the ultimate enforcer of solitude. On a clear night far from city lights, tilt your head back and look upward. Find two stars that appear to nestle against each other in the darkness, so close they seem like companions sharing the same patch of velvet black. Your eyes tell you they are neighbors. Your brain processes them as nearby points separated by a trivial gap. This is perhaps the most profound deception the universe has ever perpetrated on conscious minds. Those two stars might be separated by distances measured not in miles or kilometers, but in tens of light years. They might exist in completely different spiral arms of the galaxy. One could be a dim red dwarf, barely visible at 6 light-years distance. The other could be a brilliant blue supergiant, blazing from 800 light-years away. The night sky performs a trick of perspective so complete that it has fooled every species that ever evolved eyes capable of looking upward. It takes the incomprehensible 3-dimensional volume of space and flattens it into a dome, a ceiling decorated with lights that appear reachable, close, almost touchable. Every civilization that ever gazed at stars has been subjected to this same illusion. They look close. They look like destinations. They are not. This illusion matters profoundly because it forms the unstated foundation of every casual conversation about extraterrestrial visitors. When people imagine advanced aliens traveling to Earth, they imagine a voyage. A long one, certainly. A difficult one, absolutely. But fundamentally, a journey with a departure point, a trajectory, and an arrival. The night sky encourages this mode of thinking. It transforms stars into dots on a map, locations connected by routes, destinations linked by paths. In truth, the space between stars bears no resemblance to any journey humans have ever contemplated. It is not an ocean. Calling it an ocean insults the concept through gross understatement. The Pacific Ocean, at its widest point, stretches approximately 11,000 miles. The nearest star to our Sun sits 25 trillion miles away. You could line up the Pacific Ocean end to end more than 2 billion times and still not bridge the gap to our closest stellar neighbour. 2 billion. Try to hold that number in your consciousness without it dissolving into abstraction. This cognitive failure is not a defect in human thinking. It is a feature of how our minds evolved. Our ancestors needed to judge distances to predators, estimate the arc of a thrown spear, gauge the width of a river that needed crossing. Human visual perception calibrated itself for distances measured in feet, yards, perhaps miles on an exceptionally clear day from a mountain peak. Nothing in our evolutionary past prepared us to intuitively grasp distances measured in trillions of miles. When we look at the night sky, our brains do what evolution trained them to do. They simplify, they compress, they make the incomprehensible appear manageable. This automatic mental process has quietly corrupted every popular discussion about whether aliens could visit our world. Let us start with the closest star system to Earth. Alpha Centauri sits 4.24 light-years away. That number sounds almost friendly. 4.24. You can say it in less than a second. But a light-year is not a human unit. It is an astronomical abstraction designed to compress incomprehensible distance into something pronounceable. 1 light-year equals approximately 5.88 trillion miles. Multiply that by 4.24, and Alpha Centauri sits roughly 25 trillion miles from Earth. 25 trillion. If you began counting to 25 trillion at one number per second, never stopping to sleep or eat, you would require nearly 800,000 years to reach the end. You would start counting before anatomically modern humans had fully migrated out of Africa. Every pharaoh would rise and fall while you counted. Every empire would construct its monuments and dissolve into dust. Every war would be fought and forgotten, and you would still be counting. Still nowhere close to finished. 25 trillion miles represents the shortest possible interstellar journey from our solar system. Not the average distance, not a typical gap, the absolute minimum. Our nearest neighbour, the front door of the galaxy. And it is so monumentally far that no human-made object has crossed more than a negligible fraction of the gap. Consider Voyager 1. Launched in 1977, it is the most distant human-made object in existence. Voyager travels at approximately 38,000 miles per hour, fast by any terrestrial measure. A rifle bullet moves at roughly 1,700 miles per hour. Voyager moves approximately 22 times faster than a bullet. It has been flying for over 45 years, without stopping, without slowing, without deviating from its outbound trajectory. In all that time, Voyager 1 has covered approximately 15 billion miles. That sounds impressive until you measure it against the interstellar scale. 15 billion miles represents less than 1 light day. Not 1 light year, 1 light day. The distance light covers in 24 hours. Voyager has not yet crossed the distance that light traverses in a single rotation of Earth. A light day is 1/365th of a light year. The nearest star sits over 4 light years distant. At its current velocity, Voyager 1 would need approximately 73,000 years to reach Alpha Centauri if it were pointed in that direction. 73,000 years. Human civilization, from the first agricultural settlements to the smartphone, spans roughly 12,000 years. Voyager would need 6 times the entire span of recorded human history to reach the closest star. And when it arrived, it would not stop. It carries no braking system. It would sail past Alpha Centauri and continue into the void beyond. A frozen artifact tumbling through darkness with no destination, carrying a golden record that no one will ever play. This is the unvarnished reality of interstellar distance. Not the sanitized version from science fiction, where ships traverse light years in montages. Not the Hollywood version, where a cut bridges departure and arrival. The actual version, where our fastest spacecraft requires 73 millennia to reach the house next door. If an alien civilization launched a probe toward Earth from Alpha Centauri at comparable speeds, we would wait longer than human civilization has existed for it to arrive. And Alpha Centauri represents the closest possible starting point. Scale outward. Sirius, the brightest star in our night sky, sits 8.6 light-years away, approximately 50 trillion miles. Vega lies 25 light-years distant, roughly 147 trillion miles. Betelgeuse, the red supergiant marking Orion's shoulder, resides approximately 700 light-years from Earth. Converting that to miles produces a number so long that writing it would consume an entire line of text. These are all stars within our own galaxy, not exotic objects at the edge of the observable universe, just ordinary stars in our local galactic neighborhood. And the distances separating them already dwarf Voyager's 4-decade journey by factors that make the comparison meaningless. The Milky Way galaxy spans approximately 100,000 light-years from edge to edge. That equals roughly 588 quadrillion miles. Our solar system sits about 26,000 light-years from the galactic center, embedded in a minor spur of the Orion arm, about 2/3 of the way out from the core. Light departing one side of the galaxy requires 100,000 years to reach the opposite side. Not a spacecraft, light itself. The absolute fastest phenomenon in the universe. The cosmic speed limit that nothing with mass can ever achieve. Even light traveling at 670 million miles per hour needs 100,000 years to cross our single galaxy. A human lifespan averages roughly 80 years. Light crosses the galaxy in a time equivalent to 1,250 consecutive human lifetimes. Each of those lifetimes would begin and end in complete darkness between stars, surrounded by void, with the destination no visibly closer than at departure. And the Milky Way is just one galaxy. The nearest major galaxy, Andromeda, lies approximately 2.5 million light-years away. The observable universe contains an estimated 2 trillion galaxies scattered across 93 billion light-years of space. These numbers exist so far beyond human intuition that they function as pure abstractions rather than meaningful descriptions. No human mind can genuinely visualize 93 billion light-years. We can write it, we can calculate with it, but we cannot feel it. Here is where this matters for alien visitation. When people imagine extraterrestrial civilizations visiting Earth, they rarely consider where those civilizations would actually be located. The galaxy contains roughly 400 billion stars. Many host planetary systems. NASA's Kepler mission confirmed that planets are common, with most stars hosting at least one world. Some percentage of those systems likely contain worlds in the habitable zone, where liquid water could exist on a surface. The probability of intelligent civilizations existing somewhere in the Milky Way is not zero. It might be reasonably high. But the distribution of those civilizations across galactic space creates a problem that optimism cannot solve. If intelligent civilizations are rare, emerging around perhaps 1 in every 10 million suitable star systems, then the nearest alien civilization might be thousands of light years away. Not 4 light years, not 40, thousands. If civilizations are more common, perhaps 1 in every 100,000 suitable systems, the nearest might still be hundreds of light years distant. The galaxy is so enormous, and stars are so widely scattered, that even generous estimates of alien abundance place most civilizations at distances that are functionally unreachable. The mathematics cares nothing for hope. It cares about geometry. And the geometry of a disk 100,000 light-years wide, with stars separated by an average of 4 to 5 light-years, leaves every civilization marooned on its own island in an ocean of emptiness. Picture this. Shrink the Milky Way down to the size of North America. At this scale, each star becomes a grain of sand barely visible. Our Sun and Alpha Centauri would be 2 grains, sitting about 4 inches apart. That seems manageable. But the next nearest Sun-like star with potentially habitable planets might be several feet away. A civilization 1,000 light-years distant would be located in a different state. 5,000 light-years would place them on the opposite coast. The galaxy's full extent stretches continent to continent. The galaxy looks crowded on posters. In reality, it is defined by the emptiness between those scattered grains. Most of the map is blank space. Most of the volume contains absolutely nothing. Even if they exist, the universe itself prevents them from getting here. This is the central truth that every discussion about alien visitation must confront before considering anything else. Distance is not merely an inconvenience, it is a wall. Not a wall that engineering can tunnel through or energy can blast apart, but a wall woven into the fabric of space-time itself. The space between stars is real, physical, and enormous. It must be crossed, mile by mile, year by year. And there are trillions upon trillions of those miles between any 2 stellar neighbours. The emptiness between stars is genuinely empty, in ways difficult to appreciate from a planet's surface. The interstellar medium, the material filling gaps between star systems, has a density of roughly 1 atom per cubic centimetre. For comparison, the air you breathe contains approximately 25 quintillion molecules per cubic centimetre. The interstellar medium is roughly 25 quintillion times less dense than atmosphere. It is a vacuum more perfect than anything achievable in laboratories. It is cold, hovering just above absolute zero. It is dark, illuminated only by faint, distant starlight. It is featureless, offering no landmarks, no waypoints, no reference frames for navigation. A spacecraft travelling between stars would spend decades or centuries surrounded by nothing, traversing voids so complete that the nearest significant object in any direction would be trillions of miles away. This void creates practical problems beyond isolation. Navigation across interstellar distances requires extraordinary precision. At light-year scales, even microscopic errors in trajectory compound into enormous deviations. A navigational error of 1/10,000th of a degree at departure translates into missing the target star system by billions of miles at arrival. That is not a rounding error. That is the difference between reaching a solar system and sailing past it into emptiness with no possibility of return. Correcting course mid-journey requires energy, which requires fuel, which adds mass, which requires more energy to accelerate. Every correction feeds back into the same punishing loop. Detection presents another obstacle. Finding Earth from interstellar distances is nothing like spotting a lighthouse from a ship. Earth is a tiny rock orbiting an unremarkable star in the outer suburbs of an ordinary spiral galaxy. It has a diameter of roughly 8,000 miles, effectively invisible from even a few light-years away. It reflects a minuscule fraction of sunlight. Its most distinctive feature, the oxygen-rich atmosphere hinting at biological activity, produces spectral signatures so faint that detecting them across interstellar distances pushes the limits of any conceivable telescope. Earth's radio emissions, leaking into space since the early 20th century, form a bubble of detectability roughly 200 light-years in diameter. That bubble encompasses perhaps a few 100,000 stars. It sounds substantial until compared to the 400 billion stars in the Milky Way. Our radio bubble covers less than 1/1,000,000th of the galaxy's volume. Beyond that radius, Earth is electromagnetically silent, invisible. A civilization 1,000 light-years away would have no way to know we exist, because our signals have not reached them yet, and will not for another 900 years. And when those signals finally arrive, they will be so faint, so diluted by the inverse square law governing electromagnetic radiation, that distinguishing them from background noise becomes virtually impossible. This detection problem operates bidirectionally. If alien civilizations broadcast signals, those transmissions weaken with distance according to the inverse square law. A signal powerful at its source becomes 4 times weaker at double the distance, 9 times weaker at triple, 16 times weaker at quadruple. By the time a radio transmission crosses hundreds of light-years, it has spread across such enormous volume that the energy arriving at any point is infinitesimal. Distinguishing an alien signal from natural radio emissions of stars, pulsars, and cosmic background radiation at such distances requires either impossibly powerful transmitters or receivers of impractical scale. Consider the perspective from an alien civilization. Imagine beings on a planet orbiting a star 1,000 light-years from Earth. They are intelligent, curious, technologically advanced. Perhaps they have explored their local stellar neighborhood for millennia. They have mapped the nearest dozen star systems, sent probes to worlds orbiting close neighbors. They know their galactic suburbs' geography the way we know our solar system's layout. Now they turn attention outward. They point telescopes toward our region of space and see the Sun, an average yellow dwarf among millions of similar stars. From 1,000 light-years, the Sun does not stand out. It does not pulse with unusual signals. It exhibits no spectral fingerprints of advanced civilization. It is one ordinary star lost among countless ordinary stars. They cannot detect Earth directly. Resolving a planet Earth-size at 1,000 light-years would require a telescope with an aperture stretching hundreds of kilometers across. Even an interferometric array combining light from thousands of smaller telescopes would struggle to produce more than a single pixel of data about a world that small at that distance. They might, with extraordinary effort and extraordinary luck, detect the slight dimming of sunlight as Earth transits the Sun's face from their vantage. But this transit method only works if geometry aligns perfectly, if Earth's orbital plane intersects their line of sight. For most galactic observers, this alignment does not exist. Earth is invisible. They cannot detect our radio signals. Those signals departed Earth roughly a century ago, spreading outward at light speed in an expanding shell. That shell has covered approximately 100 light-years, reaching perhaps a few 100,000 nearby stars. A hypothetical civilization sits 1,000 light-years away. Our signals will not reach them for another 900 years. And when those signals finally arrive, they will have weakened to whispers. The power of radio transmissions drops with the square of distance. By the time Earth's strongest broadcasts cross 1,000 light-years, signal strength at any point will be billions of times fainter than cosmic background noise. From their vantage, our entire solar system, everything we have ever known or built or dreamed, is one anonymous dot among 400 billion similar dots. Invisible, unremarkable, lost in the crowd. They have no reason to come here because they have no way to know we are here. This is not a limitation of their technology, it is a limitation of physics. Light travels at a fixed speed. Information cannot outrun it. Our existence is a secret the universe keeps from them, and will continue keeping that secret for 9 more centuries, at which point it will deliver the news as a whisper, too faint to hear. Suppose they are extraordinary. Suppose they have built telescope arrays spanning thousands of kilometers. Suppose they have mapped every star within 5,000 light-years and catalogued atmospheric composition of every rocky planet in habitable zones. Suppose, against staggering odds, they have identified Earth as a world with oxygen-rich atmosphere, a possible signature of biological activity. They still do not know intelligent life exists here. Oxygen suggests biology. It does not suggest civilization. They would see what Earth looked like 1,000 years ago, because light reaching their telescopes left our planet 10 centuries before. They would see Earth of roughly 1026, medieval Europe, Song Dynasty China. No radio signals, no city lights, no spectral evidence of industrial activity. Just a small blue world with interesting atmosphere. One candidate among potentially thousands of similar worlds scattered across their observable sky. The motivation to cross 1,000 light-years of void, to visit one interesting rock among thousands of interesting rocks, is not obvious. It is not rational without evidence that the trip would yield something no closer world could provide. Even if they somehow identified Earth as compelling, even if they detected our oxygen atmosphere, or stumbled upon radio emissions after waiting centuries for arrival, they would face the crushing distance problem. 1,000 light-years equals approximately 5.88 quadrillion miles. At 10% of light speed, a velocity representing almost unimaginable engineering achievement, the journey would take 10,000 years one way. The civilization launching the mission would need to sustain interest, funding, political will, and institutional memory for 10 millennia just for the outbound leg. No human institution has lasted more than a few thousand years. Most governments rise and fall within centuries. Most empires are dust within a millennium. The mission would outlive the society that conceived it many times over. This is the optimistic scenario, assuming the alien civilization is only 1,000 light-years away, placing them among closer possible neighbors in a galaxy 100,000 light-years across. If they are 5,000 light-years away, the journey at 10% light speed takes 50,000 years. If they inhabit a star on the far side of the galactic core, it takes hundreds of thousands of years. There is a common instinct, when confronted with these distances, to reach for human analogies of exploration. People compare interstellar travel to crossing the Atlantic Ocean in the 15th century or landing on the Moon in the 20th. These comparisons feel natural because they invoke journeys that once seemed impossible but were eventually achieved through ingenuity and determination. The implication is that interstellar travel will similarly yield to future innovation. Give it enough time, enough effort, enough brilliant minds, and the stars will fall within reach, just as new continents and celestial bodies did before. This reasoning contains a fatal flaw. The Atlantic Ocean is roughly 3,000 miles wide. The Moon sits approximately 240,000 miles away. Alpha Centauri is 25 trillion miles distant. The jump from Atlantic crossing to Moon landing is a factor of roughly 80. Impressive, but within the same broad order of magnitude. The jump from Moon landing to nearest star is a factor of over 100 million. These are not steps on the same ladder. They are entirely different categories of challenge, separated by a chasm so wide that the word progress loses meaning. Crossing the Atlantic required building better ships from existing materials. Reaching the Moon required inventing rockets powerful enough to escape one planet's gravity. Reaching another star requires confronting the fundamental speed limit of the universe, the exponential energy costs of relativistic acceleration, and journey durations measured not in days or weeks, but in millennia. The progression from sailing ship to Saturn V rocket is not precedent for progression from rocket to starship. It is a comforting analogy that disintegrates the moment you examine actual numbers. The universe operates on scales that do not care about ambition, intelligence, or technological progress. The speed of light is not a barrier that more advanced physics will eventually overcome. It is a structural property of space-time woven into every equation describing how reality functions. Every particle, every wave, every interaction in the cosmos obeys this limit. It is not a wall to break through. It is the shape of the room itself. You cannot break through walls you are made of. The Milky Way might contain thousands of intelligent civilizations right now. Millions of planets might harbor complex life. The galaxy could be teeming with minds, wondering, exactly as we do, whether anyone else is out there. But every one of those civilizations sits inside its own bubble of isolation, surrounded by trillions of miles of nothing, staring at the same deceptively close stars, facing the same impossible arithmetic. The galaxy is not a neighborhood. It is an archipelago of island worlds, separated by oceans no ship has been designed to cross. Those oceans are measured not in miles, but in light years, not in hours, but in millennia. Every star is a solitary outpost. Every civilization is alone with its own sky. Distance is the first wall, the wall encountered before even considering engineering, energy, or time. The wall transforming interstellar travel from a question of willpower into a question of physics. And it stands equally high for every civilization in the universe, regardless of intelligence, cultural age, or technological development. The laws of geometry apply to everyone. But distance alone does not make the full case. A sufficiently motivated civilization might look at 25 trillion miles and say, "We accept the scale. We will build faster ships. We will push propulsion boundaries. We will aim for stars and bear whatever cost the universe demands." This is where the problem deepens, because the cost of crossing interstellar distances is measured not only in miles, but in energy. And the energy required to accelerate meaningful mass to even modest fractions of light speed is so staggering so fundamentally enormous that it makes the distance problem look like gentle introduction. Distances between stars are not large the way oceans are large or continents are wide. They are large in a way that breaks every analogy we reach for, a way that turns familiar concepts like travel and journey into abstractions barely applicable. But distance by itself does not make interstellar travel impossible. Distance is passive. It simply exists, waiting to be crossed. What makes crossing functionally impossible is what physics demands in exchange for speed. Because the only way to shrink an interstellar journey from millennia into something remotely approachable is velocity. And velocity at scales required for star travel costs energy in quantities that would bankrupt entire worlds. This is not a soft barrier, not a problem that bigger engines or better fuel gradually solves. Energy requirements for interstellar travel scale in ways fundamentally hostile to engineering. They do not grow linearly with speed, they grow exponentially. And that exponential curve is not a feature of our current technology. It is a feature of the universe itself, baked into equations of special relativity, confirmed by every particle accelerator ever built, inescapable for any civilization made of matter anywhere in the cosmos. Start with the most basic version. To travel between stars in any time frame shorter than geological ages, a spacecraft must reach a significant fraction of light speed. 10% of light speed, often written as 0.1 c, is a common benchmark in serious discussions of interstellar propulsion. At this velocity, a ship would travel roughly 67 million miles per hour. That is almost 18,000 miles per second. For comparison, the fastest human-made object relative to the Sun, the Parker Solar Probe at closest approach, reaches approximately 430,000 miles per hour. 10% of light speed is more than 150 times faster than the fastest thing humanity has ever built. It represents a leap in velocity so enormous that no incremental improvement in existing propulsion technology can bridge the gap. Consider what happens when you try to accelerate an object to this speed. Start with something modest. A robotic probe with no crew, no life support, no artificial gravity. Just instruments, communication system, power source, and frame to hold it together. Call it 1,000 kilograms, roughly the mass of a small car. To accelerate 1,000 kilograms to 10% of light speed requires approximately 4.5 times 10 to the 17th joules of kinetic energy. Written out, that is 450 quadrillion joules. This number means nothing in isolation. Anchor it to something real. A large nuclear power plant produces roughly 1 gigawatt of continuous power. 1 gigawatt equals 1 billion joules per second. Running that plant at full capacity for an entire year produces approximately 31.5 petajoules. Accelerating our tiny probe to just 10% of light speed would consume roughly 14 years of a nuclear power plant's total output. 14 years of a facility costing billions of dollars to build and powering 1 million homes, funneled entirely into pushing a car-sized object to a velocity that still means a 42-year trip to the nearest star. Widen the lens. Total energy humanity produces in an entire year from every power plant, every engine, every fire, every solar panel on Earth amounts to roughly 5.8 times 10 to the 20th joules. Energy needed to accelerate our tiny 1,000 kilogram probe to 10% of light speed is approximately 1/1300th of global annual energy production for a single probe with no deceleration capability, no crew, no return trip. Just a small machine flung into the void with enough velocity to reach the nearest star in 4 decades. The Hiroshima atomic bomb released approximately 6.3 times 10 to the 13th joules of energy. The kinetic energy of our modest probe at 10% of light speed is equivalent to roughly 7,000 Hiroshima bombs. 7,000 nuclear detonations compressed into motion of a single small spacecraft. That is the energy price for the cheapest possible interstellar ticket. Not for a crewed vessel, not for a round trip, not for a journey to distant star. Just a tiny probe aimed at the nearest star with no way to stop when it gets there. We have not yet accounted for stopping, because a probe arriving at Alpha Centauri at 10% of light speed will fly past the star system in hours unless it decelerates. Deceleration requires the same energy as acceleration applied in reverse. The energy budget just doubled. 14,000 Hiroshima bombs worth of energy for a car-sized robot to visit the nearest star and halt when it arrives. This is the scale for the simplest conceivable interstellar mission. Everything gets worse from here. The tyranny of the rocket equation governs every spacecraft carrying its own propellant. The equation, first published by Tsiolkovsky in 1903, describes brutal relationship between velocity a rocket can achieve and fuel it must carry. The core problem is circular. To go faster, you need more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that additional mass, which adds more mass, which requires more fuel. This exponential feedback loop means fuel requirements do not scale proportionally with speed. They scale exponentially. For chemical rockets, producing exhaust velocities of roughly 4.5 kilometers per second, reaching even 1% of light speed would require a fuel-to-payload ratio so extreme the spacecraft would be almost entirely fuel. Reaching 10% of light speed with chemical propulsion is not impractical. It is mathematically impossible. The fuel required exceeds the mass of the observable universe. This is not exaggeration. The exponential function grows that aggressively. Nuclear propulsion offers improvements, but does not escape the fundamental trap. A nuclear thermal rocket, heating propellant using fission reactor, achieves exhaust velocities roughly twice those of chemical rockets. A nuclear pulse propulsion system, like theoretical Project Orion concept from the 1950s, would detonate nuclear bombs behind spacecraft to generate thrust. Orion's designers estimated it could reach perhaps 3 to 5% of light speed. Even this extraordinary concept, requiring detonation of thousands of nuclear warheads in sequence, could not approach velocities needed for practical interstellar travel. Fusion propulsion represents what many regard as the most promising theoretical option beyond nuclear pulse concepts. If engineers could build working fusion reactor, converting hydrogen into helium and channeling resulting energy into directed thrust, it would represent monumental advance over chemical or fission rockets. Fusion releases roughly 4 times more energy per kilogram of fuel than fission, and hydrogen fuel is abundant. A fusion-powered starship could theoretically achieve exhaust velocities of several percent of light speed, making interstellar missions conceivable on timescales of centuries rather than millennia. But sustained, controlled fusion remains beyond human capability, despite more than 70 years of dedicated research and hundreds of billions of dollars in global investment. The fundamental challenge is containment. Fusion requires heating hydrogen isotopes to temperatures exceeding 100 million degrees Celsius, roughly 6 times hotter than the Sun's core. At these temperatures, matter exists as plasma, a state so energetic it destroys any physical container it touches. Current approaches use powerful magnetic fields to suspend plasma in vacuum, preventing contact with reactor walls. This magnetic confinement must be sustained continuously with extraordinary precision, while plasma writhes and twists in chaotic turbulence, defying reliable control for decades. The history of fusion research is a history of promises deferred. In the 1950s, physicists predicted commercial fusion power within 20 years. In the 1970s, they predicted it within 30 years. In the 2000s, they predicted it within 30 years again. The joke among plasma physicists is that fusion is always 30 years away. This is not because scientists are incompetent. It is because the physics is genuinely, stubbornly, almost maliciously difficult. As of today, no fusion reactor on Earth has produced more energy than it consumed in sustained, repeatable manner. The International Thermonuclear Experimental Reactor Project, the most ambitious fusion experiment ever attempted, aims to demonstrate net energy gain for the first time. Its construction has taken decades, and budget has ballooned to roughly $25 billion. If successful, ITER will produce approximately 500 megawatts of fusion power for periods of minutes. 500 megawatts sustained for minutes. The energy needed to accelerate even a small interstellar probe requires sustained power outputs millions of times greater, maintained not for minutes, but for months or years of continuous acceleration. The gap between current fusion research and interstellar fusion propulsion is not a gap the next generation of engineers will close. It is a chasm spanning multiple fundamental breakthroughs, each one of which may or may not prove achievable. Proposing fusion-powered starships today is like proposing skyscrapers during the Stone Age. Not merely ambitious, disconnected from current state of prerequisite technologies by unknowable number of intermediate steps. The most energy-dense fuel theoretically possible is antimatter. When matter and antimatter meet, they annihilate each other completely, converting 100% of their combined mass into energy. According to Einstein's equation, energy equals mass times speed of light squared. No other reaction in physics achieves this efficiency. Chemical combustion converts less than 1/10,000,000th of 1% of fuel mass into energy. Nuclear fission converts roughly 0.1%. Nuclear fusion converts roughly 0.7%. Antimatter annihilation converts 100%. It is the ultimate fuel, the theoretical ceiling, the maximum energy physics permits per kilogram of material. And it is still not enough to make interstellar travel easy. To accelerate a 1,000 kilogram probe to 10% of light speed using antimatter propulsion, you would need approximately 500 kilograms of antimatter combined with 500 kilograms of normal matter. That sounds surprisingly reasonable until you learn how much antimatter humanity has ever produced. The total amount of antimatter created by every particle accelerator on Earth across entire history of physics amounts to roughly 20 nanograms. A nanogram is 1/10000000th of a gram. 20 nanograms would not be visible to the naked eye. It would not register on kitchen scales. It would not register on most laboratory scales. Producing a single gram of antimatter using current technology, would require approximately $25 trillion and roughly 25 million billion watt-hours of energy. 25 trillion exceeds the gross domestic product of the United States. The energy required exceeds annual output of thousands of power plants. For 1 gram, a mass you could hold on your fingertip. Producing 500 kilograms of antimatter is not a challenge for next century or century after. It is a challenge sitting so far beyond current capability that placing timeline on it is meaningless. Scale to spacecraft large enough to carry even small crew of 10 people, along with life support systems, radiation shielding, food, water, waste recycling, navigation equipment, communication systems, structural materials. Such vessel would mass at absolute minimum hundreds of thousands of kilograms. Realistic estimates for crewed interstellar craft range from 1 million to 100 million kilograms. Antimatter fuel requirements scale proportionally. A 100 million kilogram spacecraft would need roughly 50 million kilograms of antimatter. Producing this quantity would require energy inputs so vast they exceed total energy output of current human civilization by many orders of magnitude. This is the energy wall. It does not bend. It does not soften with technological progress. It is direct consequence of physics. Kinetic energy of any object increases with square of its velocity. As velocity approaches significant fraction of light speed, relativistic effects compound the problem further. According to special relativity, as an object accelerates toward light speed, its effective mass increases. This is not metaphor. The object literally requires more energy to accelerate each additional unit of speed. At 90% of light speed, spacecraft's relativistic mass is approximately 2.3 times its rest mass. At 99%, it is roughly 7 times rest mass. At 99.9%, it exceeds 22 times rest mass. The closer you get to light speed, the more the universe resists acceleration, demanding exponentially more energy for each incremental gain in velocity. Reaching light speed itself would require literally infinite energy. It cannot be done. Not by us, not by any alien civilization, not by any being made of matter anywhere in cosmos. Put aside antimatter and consider alternative propulsion concepts not requiring onboard fuel. The most promising candidate is laser propulsion, sometimes called light sail or beam-powered propulsion. The concept is straightforward. A spacecraft carries enormous but extremely lightweight reflective sail. A ground-based or space-based laser array fires concentrated beam at sail. Photons from laser bounce off sail, transferring momentum and gradually accelerating craft. No onboard fuel required. Energy source stays at home, eliminating tyranny of rocket equation entirely. This sounds like solution. It simply trades one set of impossible engineering constraints for another. The Breakthrough Starshot initiative, announced in 2016, proposed exactly this approach. The plan envisioned fleets of gram-scale probes, each weighing roughly 1 gram, propelled by ground-based laser array, with total power output of approximately 100 gigawatts. 100 gigawatts is roughly total electrical generating capacity of a medium-sized country like the United Kingdom. This entire national energy output, focused into coherent laser beam and aimed at a sail smaller than bedsheet, would accelerate 1 gram probe to 20% of light speed, reaching Alpha Centauri in roughly 20 years. 1 gram. Not crude vessel, not even useful robotic probe by most standards. A chip-sized sensor package weighing less than paperclip. And it requires focused energy output of entire industrialized nation to reach target star in 2 decades. Scaling this concept to anything resembling meaningful spacecraft, even modest 10-kilogram probe carrying camera and communication antenna, would require laser arrays producing tens of thousands of gigawatts, more energy than human civilization currently produces. This approach carries fundamental flaw no amount of power can fix. The laser can only push. It cannot pull. A light sail, accelerated to 20% of light speed, has no way to slow down at destination. It screams past target star system in hours, taking few blurry photographs before vanishing into interstellar void. To decelerate, you would need second laser array at destination, which means someone already been there to build it, which means you have not solved the problem, merely assumed it away. Here is where argument takes critical turn. Everything discussed so far applies to human technology and human energy production. The natural response is to imagine alien civilization far more advanced than ours. A civilization that has harnessed full power of its star or developed energy sources we cannot conceive. Would such civilization not find interstellar travel affordable? Would not the energy wall crumble before their superior capabilities? No. And this is the point casual speculation consistently misses. The energy wall is not artifact of human limitations. It is consequence of physics. The kinetic energy required to accelerate mass to relativistic speeds is determined by mass of spacecraft and speed of light. These are constants. They do not change based on who is doing engineering. A civilization 10,000 years more advanced than humanity still must obey relationship between kinetic energy, mass, and velocity. They can build more efficient engines, they can harness more total energy, but they cannot reduce energy required for trip itself because that energy is dictated by laws of mechanics and relativity, not by sophistication of engine. Consider analogy from everyday physics. Lifting 1 kilogram object 1 meter against Earth's gravity requires approximately 10 joules of energy. This is true whether you lift it with hand, pulley, or robotic arm designed by most advanced engineers in history. The mechanism changes, the energy requirement does not. You can make lifting process more efficient. You can waste fewer joules on friction and heat, but you cannot reduce the 10 joules required by gravitational potential itself. The universe sets minimum cost. Technology determines only how close you can approach that minimum, never how far below it you can go. Same principle applies to interstellar propulsion. Minimum energy to accelerate 1 kilogram to 10% of light speed is approximately 4.5 times 10 to the 14th joules. No technology can reduce this number. It is set by mass, velocity, and constant speed of light. An alien civilization could theoretically approach this minimum with near-perfect efficiency, losing almost no energy to waste heat or exhaust inefficiency. But they cannot go below it. The floor is set by physics, not engineering. This means even civilization capable of capturing entire energy output of its host star, a Dyson sphere civilization producing roughly 4 times 10 to the 26th watts, would still face meaningful constraints when launching interstellar missions. Energy to accelerate crude vessel to relativistic speed would consume measurable fraction of even this godlike energy budget. Not trivial fraction either. Large interstellar arc massing millions of kilograms and accelerating to significant percentage of light speed would require energy inputs comparable to total output of star sustained over days or weeks. Single mission would be enormous undertaking, even for civilization that has mastered stellar-scale engineering. Launching thousands of such missions, the kind of exploration program needed to systematically visit star systems across galaxy, would strain resources at level making such programs effectively impractical. Even for most advanced imaginable civilization bound by known physics. The energy barrier does not soften with better technology. Thermodynamics applies everywhere in this universe. It applies to us, it applies to them. It applies to every civilization that has ever existed or ever will exist in this cosmos. There is another dimension to energy problem often overlooked. So far, we have discussed only energy required for propulsion. But sustaining spacecraft over interstellar distances demands continuous energy expenditure beyond thrust alone. Life support systems must operate without interruption for years, decades, or centuries. Temperature regulation must maintain livable conditions against near absolute zero cold of interstellar space. Communication systems must generate signals powerful enough to reach home across light years. Navigation instruments must remain operational throughout journey lasting longer than most civilizations endure. Shielding systems must protect crew and equipment from cosmic radiation, high-energy particles, and micrometeorite impacts, becoming catastrophic at relativistic speeds. Each system draws power, each imposes mass. Each feeds back into propulsion equation, demanding more fuel, which adds more mass, which demands still more energy. Total energy budget for crewed interstellar mission is not simply kinetic energy of acceleration and deceleration. It is sum of propulsion energy, life support energy, shielding energy, communication energy, and every other system that must function continuously for duration of voyage. When all factors are included, energy requirements climb even further beyond already staggering propulsion costs. A crewed interstellar mission is not merely engineering project, it is sustained industrial operation that must function autonomously, without resupply, without maintenance from external sources, without error for periods exceeding lifespan of every human institution ever created. So we arrive at full scope of what physics demands from any civilization contemplating journey to another star. They do not face single challenge, they face cascade of interlocking challenges, each one individually formidable, each one amplifying others. More speed requires more energy requires more fuel requires more mass requires more energy, more distance requires more time requires more life support requires more mass. The loop has no exit. It is not circle that better technology makes smaller. It is circle whose diameter is set by physical constants of universe. You can run around it more efficiently, but you cannot shrink it. This separates energy barrier from ordinary engineering challenges. When humans wanted to fly, they needed to generate enough lift to overcome gravity. That was engineering problem with engineering solutions. When humans wanted to reach orbit, they needed to achieve specific velocity against specific gravitational field. That was harder engineering problem with harder engineering solutions. When any civilization wants to reach another star, they need to generate energy on scale fixed by mass of their ship and immutable speed of light. This is not engineering problem waiting for better engineer. This is universe stating its price. And the price is non-negotiable. Distance sets stage. Energy sets price. Every civilization looking at stars and dreaming of crossing void must eventually do the math. And math is unforgiving. It does not offer discounts for ingenuity or exemptions for ambition. Energy required to send mass between stars is enormous, non-negotiable, universal. It applies to silicon-based life and carbon-based life, and any form of life occupying physical space and obeying laws of thermodynamics. Every alien civilization in Milky Way, no matter how ancient or advanced, faces same equation when they look toward our sun and wonder whether trip is worth cost. Most of them, if they exist, have probably done the math, and most have probably reached same conclusion. The cost is real. The distance is vast. The energy is staggering. But suppose civilization accepts cost. Suppose they commit resources of entire world or entire star to construction and launch of interstellar vessel. Suppose ship is built, fuel is loaded, crew is aboard, engines ignite with fury of small sun. Ship accelerates. It reaches 10% of light speed. Star behind shrinks to point. Star ahead remains point. Journey has begun. This is where problem deepens beyond what distance or energy alone could impose. Because even after paying impossible energy price, journey itself introduces category of obstacles no engine can overcome and no shield can fully deflect. The obstacle is time. The unrelenting, irreversible, civilization-eroding passage of time. And time, unlike distance and energy, cannot be compressed, stored, or traded. It simply passes, and it passes for everyone. The void between stars is incomprehensibly vast. Energy required to cross that void is staggering beyond any civilizational budget. But both barriers, distance and energy, are in some sense static. They can be measured, quantified, placed on ledger. Civilization could theoretically look at numbers, accept cost, and commit. The third barrier is different. It does not sit still. It does not wait on balance sheet to be evaluated. It moves. It erodes. It degrades everything it touches. The third barrier is time. And time is the cruelest constraint of all, because it attacks not just mission, but civilization that launched it, crew that flies it, ship that carries them, and very purpose that justified voyage in the first place. Begin with concrete example. 10% of light speed represents ambitious but theoretically conceivable velocity for interstellar travel. At this speed, spacecraft covers roughly 67 million miles per hour, fast enough to cross diameter of Earth's orbit around Sun in under 3 hours. Fast enough to traverse entire solar system from Sun to Neptune in roughly 2.5 days. By any human standard, 10% of light speed is blindingly fast. It is velocity at which very concept of distance seems to compress. And yet, at 10% of light speed, journey to Alpha Centauri, nearest star system at 4.24 light-years, takes 42 years. One way. Not round trip, just getting there. Crew departing Earth at age 30 arrives at age 72, assuming nothing goes wrong, assuming ship functions flawlessly for over 4 decades, assuming human body endures conditions of deep space travel without catastrophic degradation. Return trip doubles timeline to 84 years. Mission to nearest star and back would consume entire human lifetime. Person who steps onto ship is not person who steps off. They have aged beyond recognition. Everyone they knew on Earth has aged with them or died. Their children have grown old. Their grandchildren have grown old. The world they left has changed in ways they cannot predict or prepare for. They return as strangers to civilization that may have moved on without them. This is best case. Alpha Centauri is closest star. Most stars in the Milky Way are not 4 light-years away. They are hundreds or thousands of light-years distant. Scale math accordingly. At 10% of light speed, journey to star 100 light-years away takes 1,000 years. Star 500 light-years away takes 5,000 years. Star 1,000 light-years away takes 10,000 years. These are not travel times any individual can survive, not travel times any crew can endure. They are durations exceeding lifespan of every empire, every religion, every language, every cultural tradition humanity has ever produced. 10,000 years ago, human beings had not invented writing. They had not built cities. They had not domesticated horses. The entire arc of recorded human civilization, every book ever written, every war ever fought, every scientific discovery ever made, fits within travel time for a single interstellar journey at 10% of light speed to moderately distant star. Civilization launching such mission must somehow ensure mission continues functioning, continues navigating, continues pursuing objective across time span during which everything defining that civilization will transform beyond recognition or cease to exist entirely. Reduce speed. 10% of light speed is extraordinarily ambitious. Energy requirements make clear that achieving even this velocity demands resources on planetary or stellar scale. More realistic velocity for large crewed vessel, accounting for fuel mass, structural limitations, engineering constraints, might be 1% of light speed. At this speed, roughly 6.7 million miles per hour, nearest star is 424 years away. Star 100 light-years distant requires 10,000 years. Star 1,000 light-years away requires 100,000 years. At 1% of light speed, interstellar travel does not merely challenge human timescales, it obliterates them. Journey durations enter geological territory. 100,000 years ago, Homo sapiens shared planet with Neanderthals. No human structure, institution, or technology has survived 100,000 years. Nothing we have built has lasted even fraction of that time. Oldest known constructed building on Earth is roughly 12,000 years old. Oldest known continuous institution is perhaps 5,000 years old. 100,000 years is not human timescale. It is evolutionary timescale. Species change over such periods. Continents shift. Ice ages begin and end. Very concept of mission lasting this long is not engineering. It is fantasy, disconnected from every observable reality about how complex systems behave over time. This is where concept of generation ships enters conversation. The idea is straightforward. If no individual can survive journey, perhaps population can. Build vessel large enough to sustain self-reproducing community across centuries or millennia. Original crew lives, reproduces, dies aboard ship. Their descendants continue journey. Generation after generation born, lives, dies in transit, each one carrying mission forward until final generation arrives at destination. It is elegant concept in abstract. In practice, it is catalogue of cascading failure modes. Start with biology. Generationship must maintain genetically viable population across hundreds or thousands of generations. Genetic studies suggest minimum viable population for long-term survival, avoiding inbreeding depression, maintaining sufficient genetic diversity to adapt to new environments, requires at least 5,000 to 10,000 individuals. Some estimates place number higher. This is not skeleton crew of brave volunteers. This is small city. Housing, feeding, sustaining 10,000 people in closed environment for millennia requires ship of enormous size and complexity. Mass of such vessel pushes energy requirements for acceleration into territory making already impossible numbers look conservative. But population size is only beginning of biological challenge. Closed ecosystem must recycle all resources perfectly: water, air, food, waste. Every molecule must be accounted for and reprocessed indefinitely. No closed ecological system has ever been sustained by humans for more than few years. Biosphere 2, most ambitious attempt at sealed ecosystem on Earth, lasted 2 years before oxygen levels dropped to dangerous lows and system required external intervention. That experiment involved 8 people in 3-acre enclosure on Earth's surface with gravity, sunlight, functioning magnetosphere. Generationship would need to sustain thousands of people in sealed metal container hurtling through vacuum at millions of miles per hour, with no sunlight, no natural gravity, no magnetic shielding, no possibility of outside help, for thousands of years, without single critical system failure. Social dimension is equally catastrophic. Human societies are not stable across millennia. They fragment, reorganize, collapse, with regularity historians have documented exhaustively. They experience revolutions, civil wars, ideological shifts, cultural drift, transforming community beyond recognition within few generations. Imagine reality aboard generationship 500 years into 10,000-year voyage. Original crew is 20 generations dead. Their names survive in database somewhere, perhaps in memorial hall fewer people visit with each passing century. No one aboard has ever seen sky, felt wind, stood beside ocean. Mission was conceived by people so distant in time they might as well be mythological figures. Their language has drifted. Words they use to describe mission's purpose have shifted meaning through centuries of isolation. Cultural references have mutated beyond recognition. Music they listened to, stories they told, values they held, have been replaced by new traditions born inside ship, traditions unrecognizable to founders. Ship's social structure has reorganized multiple times through crises, power struggles, ideological movements original planners never anticipated. Some factions believe mission is sacred, divine mandate inherited from ancestors who saw truth current generation must honor. Others believe mission is prison sentence imposed by long-dead tyrants who had no right to condemn descendants to life inside metal tube. Third faction has developed religious framework, reinterpreting journey entirely, teaching ship has always existed. Idea of origin world is comforting myth. Concept of destination is heretical fantasy, designed to distract faithful from only reality that matters, ship itself. These factions compete for control of resources, ships' governance systems, educational curriculum shaping next generation's understanding of why they exist and where they are going. Some conflicts resolve through debate and compromise, others will not. Violence is not merely possible aboard Generation's ship over millennia. Given length of time, pressure of confinement, absence of any external moderating influence, it is statistically inevitable. Extend timeline: 1,000 years into voyage, 2,000, 5,000. At each milestone, social pressures intensify. Resources abundant at departure have been consumed, recycled, consumed again, gradually degraded through imperfect recycling. Ships' population has fluctuated through epidemics, famines caused by agricultural system failures, periods of deliberate population reduction when resources ran scarce. Original governance structure has been overthrown and replaced dozens of times. Mission's purpose has been reinterpreted so many times it bears no resemblance to original mandate. Destination star, still thousands of years away, is abstraction holding no emotional weight for people who have lived entire lives, whose parents and grandparents and great-grandparents lived entire lives, inside same corridors and chambers. Journey is no longer means to end. It is only world anyone has ever known. And suggestion this world should someday end, that ship should stop, and population should disembark onto alien planet with open sky and unknown dangers, might be met not with excitement, but with terror, resistance, outright refusal. Population confined to finite space with no external contact, no immigration, no new resources, no horizon beyond vessel walls, faces psychological pressures no human community has ever been tested against. What happens when birth rates fall below replacement levels because population collectively decides, consciously or unconsciously, that bringing children into sealed metal world with no future beyond more sealed metal is act of cruelty rather than hope? What happens when critical specialist dies without having trained successor and knowledge needed to maintain vital system is lost forever? What happens when ship's manufacturing capability degrades to point where replacement parts can no longer be produced and each mechanical failure becomes permanent? These are not hypothetical concerns. They are projections based on observed human behavior in far less extreme conditions. Isolated communities on Earth, communities with access to fresh air, sunlight, possibility of leaving, still experience social collapse, violence, ideological fragmentation within few generations. Mechanical degradation poses yet another existential threat. No machine lasts forever. Every material degrades over time. Metals fatigue, seals erode, electronics fail, lubricants break down, radiation damages circuitry and structural components alike. Generation ship must maintain every critical system: propulsion, navigation, life support, power generation, radiation shielding, hull integrity, across timescales exceeding operational lifespan of any machine humans have ever built by orders of magnitude. Longest operating human-made machines have lasted perhaps few centuries under favourable conditions on Earth's surface. Generation ship must operate in most hostile environment imaginable. Hard vacuum, cosmic radiation, extreme temperature differentials, micrometeorite bombardment, for thousands of years without resupply. Every component must either be replaced using onboard manufacturing capabilities or designed to endure conditions no known material can withstand indefinitely. Even if they exist, universe itself prevents them from getting here. Time does not merely create logistical problems for travelers. It creates fundamental disconnect between mission and civilization that launched it. Consider civilization sending crewed vessel toward Earth from star 1,000 light-years away, traveling at 10% of light speed. Journey takes 10,000 years. During those 10,000 years, home civilization continues to exist, evolve, change. Technologies advance, social structures transform, values shift. Civilization that launched mission 10,000 years ago may bear no resemblance to civilization existing when ship arrives. It may have collapsed entirely, leaving behind ruins and silence. It may have transcended into forms unrecognizable to original planners. It may have developed faster propulsion technologies and sent second mission arriving before first one. Ship becomes artifact, relic of obsolete era, still crawling toward destination while civilization that built it has moved on or disappeared entirely. This is not speculation, it is extrapolation from observed patterns. Human technological capability has increased exponentially over the past few centuries. If this pattern holds for any civilization, then mission launched today using best available technology will be obsolete long before arrival. Civilization launching interstellar mission faces paradox. If they wait, technology improves and future mission could arrive sooner. But if they always wait, they never launch. And if they launch now, mission may be overtaken by faster ship launched centuries later. This is sometimes called incessant obsolescence postulate, and it creates rational disincentive for any civilization to commit resources to interstellar travel. Optimal strategy is always to wait for better technology, but waiting indefinitely means never going at all. Communication delay compounds every one of these problems into something approaching total futility. At interstellar distances, speed of light imposes hard limit on information transfer, just as absolute as speed limit on physical travel. Radio signal or laser communication beam travels at light speed, meaning it takes 1 year to cross 1 light year. Message sent from Earth to star 100 light-years away takes 100 years to arrive. Reply takes another 100 years to return. Single exchange of information requires 200 years. Imagine what 200-year conversation actually looks like in practice. Civilization launches mission to star 100 light-years away. 10 years after departure, Homeworld discovers critical design flaw in ship's radiation shielding. They immediately transmit warning with detailed repair instructions. That message, traveling at light speed, chases ship across void. But ship is also moving at 10% of light speed in same direction. Message gains on ship gradually, closing gap at 90% of light speed. It takes roughly 11 years to catch up. By time crew receives warning, they have been flying with degraded shielding for 21 years. Cumulative radiation exposure may have already caused irreversible biological damage. Repair instructions reference tools and materials available at launch, but since consumed or repurposed. Crew sends reply explaining situation and requesting alternative solutions. That reply takes over 11 years to reach home. Engineers who discovered original flaw are now 32 years older. Some have retired, some have died. Institutional knowledge needed to devise alternative solution may have migrated to new generation of engineers unfamiliar with ship's specific configuration. They develop workaround and transmit it. Another 11+ years pass. By time crew receives revised instructions, more than 50 years have elapsed since original flaw was discovered. Crew members who first received warning are elderly or dead. Their replacements must interpret instructions written for version of ship modified and repaired many times in intervening decades. This is what interstellar communication looks like at 100 light-years. Not conversation, series of messages in bottles, each one arriving too late to matter, each one referencing reality that no longer exists. At 1,000 light-years, situation becomes absurd. Signal takes 1,000 years to arrive. Reply takes another 1,000 years to return. Single exchange of information requires 2,000 years. Civilization that sent original message may not exist when reply arrives. Language message was written in may have evolved into something unrecognizable. Communication channel itself, frequency, encoding, protocol, may have been abandoned centuries ago, replaced by technologies original senders never imagined. Reply arrives to audience that cannot read it, transmitted by sender that no longer exists. About problem either solved or became irrelevant millennia before response was composed. For mission in transit, communication delay means total autonomy from moment of departure. For all practical purposes, ship travelling to star 1,000 light-years away cannot receive updated instructions from home in meaningful time frame. Within few decades of departure, communication lag renders real-time coordination impossible. Within few centuries, even slow-paced exchanges of information become impractical. Mission is on its own. Every decision must be made locally. Every problem must be solved without external help. Every crisis must be managed by crew or ship's autonomous systems with no possibility of consultation, reinforcement, rescue. Ship becomes isolated civilization unto itself, disconnected from origin, permanently. If ship encounters catastrophic problem, no one is coming to help. If mission succeeds, no one from launching civilization may be alive to receive news. Layer interstellar medium itself onto this picture. Space between stars is functionally empty in terms of matter density, but empty does not mean harmless. At relativistic speeds, sparse material scattered through interstellar space becomes lethal hazard. Grain of dust weighing 1 milligram, striking spacecraft at 10% of light speed, delivers kinetic energy equivalent to roughly 100 kilograms of TNT. That is single dust grain, not rock, not pebble. Particles smaller than grain of table salt hitting with force of large conventional bomb. Interstellar medium contains roughly 1 dust grain per 100,000 cubic meters in denser regions near galactic plane. Over journeys spanning light years, spacecraft with cross-sectional area of just few hundred square meters would encounter thousands of such particles. Each impact would deliver explosive force to hull. But it is not just individual impacts threatening vessel. It is cumulative effect of trillions of microscopic collisions over years and decades of flight. At 10% of light speed, individual hydrogen atoms, most common element in interstellar space, strike hull with energies in mega-electron-volt range. Each individual atom deposits tiny amount of energy, but flux is relentless. Every second, every minute, every hour, every year, for decades or centuries, front face of spacecraft is being sandblasted by stream of particles moving at relativistic velocities. This transforms sparse hydrogen gas of interstellar medium into steady bombardment, functionally equivalent to standing inside low-level particle accelerator. Over years and decades of exposure, this radiation erodes surface materials at molecular level, degrades crystalline structures of metals, damages electronic components through accumulated displacement of atoms within semiconductors, poses severe health risks to any biological crew through chronic radiation exposure. Shielding against this bombardment is theoretically possible, but demands material thick enough and dense enough to absorb mega-electron-volt level impacts continuously for decades. Mass penalty is severe. On vessel where every kilogram already represents enormous energy investment, cost of adequate protection may exceed what any realistic design can bear. Cosmic rays present additional hazard no shielding can fully eliminate. High-energy cosmic ray particles, primarily protons, accelerated to near light speed by astrophysical processes like supernova remnants and active galactic nuclei, penetrate virtually any material. Some particles carry energies equivalent to fast-pitched baseball concentrated into single subatomic particle. They pass through spacecraft hulls, through shielding, through human tissue, breaking molecular bonds and damaging DNA as they go. Long-duration spaceflight within our own solar system already poses significant cancer risks from cosmic ray exposure. Interstellar travel, lasting decades or centuries, would subject crews to cumulative radiation doses far exceeding safe limits. No known material provides complete protection. Even meters of solid lead merely reduce flux without eliminating it. For journeys lasting thousands of years aboard generation ships, cosmic ray damage to both biological organisms and electronic systems represents slow, relentless degradation, compounding with every passing year, never pausing, never reversing, always accumulating. Time is not a resource that can be manufactured. It passes. Civilizations rise and fall. Stars are born and die. Universe does not pause for travelers. There is one more temporal dimension that must be addressed. Relativistic time dilation, confirmed consequence of special relativity, alters flow of time for objects moving at significant fractions of light speed. Crew traveling at 90% of light speed would experience time passing at roughly 44% of rate experienced by observers who remain stationary. Journey taking 100 years in reference frame of home civilization would feel like approximately 44 years to crew. At 99% of light speed, dilation factor increases dramatically. Crew would experience only about 14 years for every 100 years passing at home. This sounds like a solution. If time passes more slowly for travelers, they could survive longer journeys. And, in narrow technical sense, this is true. Crew traveling at 99% of light speed to star 100 light-years away would experience only about 14 years of subjective time. They would arrive biologically intact, still young enough to explore destination. But time dilation solves problem for travelers while catastrophically amplifying it for everyone else. While 14 years pass aboard ship, 100 years pass on homeworld. Crew arrives at destination to find everyone they knew is dead. Civilization they left behind has had full century to change, evolve, collapse, forget about them. Any mission relying on time dilation to make interstellar travel survivable for crew simultaneously guarantees mission becomes irrelevant to civilization that launched it. Crew experiences manageable journey. Home civilization experiences absence measured in centuries. Messages sent home arrive decades or centuries after departure. Replies, if they come at all, arrive decades or centuries after that. Crew exists in temporal bubble, aging slowly while universe ages normally around them. They are not just traveling through space, they are traveling forward through time, arriving in future that did not wait for them. And reaching 99% of light speed brings us crashing back into energy wall, magnified to almost inconceivable degree. Relativistic mass increase at this velocity means energy required for acceleration is not merely doubled or tripled, it is multiplied by factor of roughly 7 compared to rest mass energy budget. Fuel requirements, engineering tolerances, shielding demands, everything escalates by nearly order of magnitude. Time dilation does not come free. It is purchased at cost of exponentially greater energy expenditure, which is already beyond budget of any civilization bound by known thermodynamics. This creates deeply uncomfortable conclusion. At achievable speeds, journeys take so long, missions outlive civilizations. At extreme speeds, time dilation compresses journey for crew but demands energy, making trip effectively impossible to launch. There is no sweet spot. No velocity at which interstellar travel becomes simultaneously affordable and timely. Universe has arranged its constants with precision, blocking every attempted shortcut. Every solution to one constraint tightens others. Reduced travel time and energy cost explodes. Add shielding against radiation and mass grows. Increase mass and fuel requirement spirals. Extend mission duration and crew, ship, civilization behind it all begin to crumble. No single breakthrough breaks pattern, because pattern is not chain with weakest link. It is web, where every strand reinforces every other strand. And web is woven from fundamental constants of universe. Civilization 1,000 light-years from Earth, wanting to send mission here, must solve every one of these problems simultaneously. They must generate enough energy to accelerate vessel to significant fraction of light speed. They must build ships surviving millennia of operation in harshest environment imaginable. They must maintain crew or self-sustaining population across timescales exceeding lifespan of every civilization in their own history. They must navigate with precision across distances so vast that errors of fractions of degree result in missing target by billions of miles. They must shield against dust, radiation, cosmic ray bombardment, intensifying with velocity. They must accept communication with home becomes impossible within centuries of departure. They must accept civilization they represent may not exist when they arrive. And they must do all this for destination they cannot confirm is worth visiting. At 1,000 light-years, no telescope can resolve civilization on planet's surface. No electromagnetic evidence of our existence has had time to cross gap. They would be committing 10,000 years of resources and lives to reach world that, for all they know, is barren rock. Each requirement is individually daunting. Together, they form barrier not weakening with technological advancement, because underlying constraints are set by physics, not engineering. Better engines do not shorten distance. Faster ships do not eliminate radiation hazards. More advanced life support does not prevent social collapse across millennia. Stronger materials do not stop universal tendency of all organized systems to decay over time. Obstacles are layered, interlocking, grounded in bedrock of physical law. There is one final argument always surfacing at this point in conversation. It looks at distance, energy, time, and says, "You are thinking too small. You are projecting human limitations onto alien civilizations. Civilization millions of years more advanced than us would have technologies we cannot imagine. They would find ways around these barriers we are too primitive to conceive. They would simply be more advanced." This argument has intuitive appeal. It feels humble. It feels open-minded. It feels like it respects vastness of possibility. It is also wrong. And reasons why cut to very heart of what laws of physics actually are. Every barrier explored in this documentary, distance, energy, time, invites same rebuttal. It arrives in conversations, in comment sections, in late-night debates between friends staring at stars. Rebuttal sounds reasonable. It sounds humble. It sounds like kind of open-minded thinking serious people should embrace. It goes like this. You are thinking like human. You are projecting our limitations onto beings who may have had millions of years to advance beyond us. Civilization that old, that intelligent, that far beyond our comprehension would have solved problems we cannot even articulate yet. They would find a way. They always find a way. This argument feels powerful because it appeals to imagination. It invokes unknown and weaponizes it against constraint. It says, in essence, that because we do not know everything, anything is possible. But this reasoning contains flaws so fundamental it undermines entire premise. Constraints described throughout this story are not human limitations. They are not artifacts of our primitive technology or limited understanding. They are properties of universe itself. Speed of light is not human speed limit. It is cosmic speed limit. Relationship between mass, velocity, kinetic energy is not human equation. It is universal equation. Second law of thermodynamics is not human observation about entropy. It is law governing every physical process that has ever occurred or ever will occur anywhere in cosmos. These constraints do not care who is doing engineering. They apply to carbon-based life, silicon-based life, energy beings, digital consciousnesses, every other form of intelligence occupying physical space and manipulating physical matter. Universe wrote rules before any civilization existed to read them. Begin with most structured version of advanced civilization argument. In 1964, Soviet astronomer Nikolai Kardashev proposed scale for classifying civilizations based on total energy consumption. Type 1 civilization harnesses all energy available on its home planet, roughly 10 to 16th watts for Earth-sized world. Type 2 civilization harnesses entire energy output of its host star, roughly 4 times 10 to 26th watts for Sun-like star. Type 3 civilization harnesses energy output of its entire galaxy, roughly 4 times 10 to 36th watts for Milky Way-sized galaxy. Humanity currently sits at approximately 0.7 on this scale. We do not yet capture all energy reaching Earth from Sun, let alone Sun's total output. Kardashev scale is often invoked to suggest sufficiently advanced civilizations would find interstellar travel trivial. Type 2 civilization commanding full power of star should be able to launch starships way we launch satellites. Type 3 civilization harnessing entire galaxy should be able to scatter probes across cosmos like seeds on wind. Energy wall described earlier would crumble before such staggering power. Or so argument goes. But this reasoning confuses total energy available with energy required for specific task. Type 2 civilization has access to enormous power. That is not in question. What is in question is whether that power changes physics of trip itself. An answer is no. Minimum kinetic energy required to accelerate given mass to given velocity is fixed by relationship between mass, velocity, speed of light. No amount of available power reduces this minimum. Type 2 civilization can generate energy more easily than we can. They can afford fuel bill more comfortably, but they cannot pay smaller bill. Bill is set by physics, not economics. Harnessing power of entire star means you can write bigger check. It does not mean check is smaller. Consider what this means in practical terms. Crude interstellar vessel massing 10 million kilograms, modest by standards of any ship intended to sustain population across interstellar distances, requires roughly 4.5 times 10 to 21st joules to reach 10% of light speed. Type 2 civilization, harnessing full output of its star, could generate this energy in fraction of second. But this fact is less reassuring than appears, because energy was never deepest constraint. Speed of light is. 1% of star's annual energy for single ship travelling at modest fraction of light speed. Type 2 civilization could afford this, but launching fleet of such vessels, kind of systematic exploration program needed to visit even small fraction of nearby star systems, would consume significant portion of their stellar budget. And each ship still faces every other constraint described in this story. Each ship still takes centuries or millennia to reach destination. Each ship still faces interstellar hazards, communication blackouts, mechanical degradation, slow erosion of time. More energy does not make ship go faster than light. More energy does not stop clock. More energy does not smooth void between stars or sweep away dust and radiation filling it. Even Type 3 civilization, commanding energy of 400 billion stars, faces same structural constraints, multiplied across larger canvas. They can launch more missions, they can build more ships. But each mission still obeys same physics. Each ship still crawls through void at sublight speeds, still ages, still degrades, still arrives at destinations that may have changed beyond recognition during journey. Galactic scale energy does not bypass relativistic limits. It does not compress distance between stars. It does not exempt matter from laws of thermodynamics. It simply means civilization can attempt more missions simultaneously, each one individually subject to every constraint making trip functionally impossible for lesser civilization. More energy does not change speed limit. It does not eliminate time dilation. It does not remove interstellar dust. Rules apply to everyone. Address proposals claiming to circumvent physics entirely rather than merely overpowering it. Warp drives, wormholes, faster than light travel. These concepts populate science fiction with such regularity, many people assume they represent genuine scientific possibilities, awaiting only sufficient technological advancement. They do not. Warp drive concept, most famously formalized by physicist Miguel Alcubierre in 1994, proposes contracting space in front of vessel and expanding it behind, creating bubble of warped space-time, carrying ship faster than light, without ship itself exceeding light speed through its local space. Mathematics are internally consistent within general relativity. Physics, however, are devastating. Alcubierre drive requires exotic matter with negative energy density to sustain warp bubble. Negative energy density means matter weighing less than nothing, gravitationally repelling rather than attracting. No such material has ever been observed. No theoretical framework produces it in usable quantities. Energy required to create and sustain warp bubble in early calculations exceeded mass energy of entire observable universe. Later refinements reduced this to merely mass energy of Jupiter, which remains approximately 10 to 27th kilograms converted entirely to energy. This is unsupported by experimental evidence at every level. It requires materials that do not exist, energies that cannot be produced, conditions never observed in nature. Calling it speculative is generous. It is mathematical curiosity within general relativity, not blueprint for engineering. Wormholes face similar objections. Wormhole or Einstein-Rosen bridge is theoretical tunnel through spacetime connecting two distant points. If stable, traversable wormholes could be created and maintained, they would indeed allow instantaneous travel between distant locations. But every known solution to equations of general relativity, producing wormhole, also requires exotic matter with negative energy density to hold wormhole open. Without this material, wormhole collapses faster than any object could pass through it. Same, exotic matter, never observed, never produced, may not be physically possible. Additionally, traversable wormholes would likely violate causality, principle that causes precede effects. If you can travel instantaneously between distant points, you can, through straightforward application of special relativity, arrive at destination before you departed. This creates time travel paradoxes most physicists regard as strong evidence traversable wormholes cannot exist. Universe appears to enforce what physicists call chronology protection conjecture, as yet unproven but widely suspected principle that laws of physics conspire to prevent time travel. Wormholes are unsupported by experimental evidence and face deep theoretical objections, going beyond mere engineering difficulty. Faster-than-light travel of any kind faces same fundamental obstacle. Special relativity does not merely say nothing currently goes faster than light. It says structure of space-time forbids it for anything with mass. Speed of light is not velocity limit in way speed limit on highway works where you could theoretically build faster car but choose not to. It is structural feature of how space and time relate to each other. As any massive object approaches light speed, energy required to accelerate it further approaches infinity, not very large finite number, actual mathematical infinity. You cannot reach infinity. You cannot exceed it. You cannot engineer around it. Speed of light is geometry of universe, and you cannot build machine violating geometry. These are not limitations of current knowledge future discoveries might overturn. They are consequences of most thoroughly tested theories in history of physics. Special relativity has been confirmed by every experiment ever designed to test it, across more than a century of increasingly precise measurements. General relativity has been confirmed by gravitational lensing, gravitational waves, precession of Mercury's orbit, behavior of GPS satellites, hundreds of other observations. Speed of light as absolute limit is not provisional hypothesis awaiting revision. It is one of most firmly established facts in all science. Could future physics reveal something unexpected? In principle, yes. Any scientific conclusion is subject to revision in light of new evidence. But probability future discoveries will overturn speed of light limit is comparable to probability future biology will overturn germ theory of disease. Not zero, but so close to zero that building argument on it is not open-mindedness. It is wishful thinking wearing costume of humility. There is another temporal dimension advanced civilization argument consistently fails to address. Civilizations do not last forever. They rise, they flourish, they decline, they collapse or transform into something unrecognizable. Human history provides ample evidence of this cycle, and there is no reason to believe alien civilizations are exempt. Window during which civilization possesses technology to attempt interstellar travel may be remarkably narrow. Humanity has been industrial, electronically communicating species for roughly 250 years. We are only example we know. If that window is typical or even generous, then period of interstellar capability is brief flash against billions of years planet may orbit its star. Civilization must develop technology, master resources, launch mission within that flash, or opportunity closes forever. Interstellar travel at achievable velocities requires mission durations of thousands to tens of thousands of years. This means mission must outlast civilization that launches it, not by small margin, by orders of magnitude. Civilization existing for 10,000 years, already extraordinarily long-lived society by any historical standard, would need to launch mission taking 10,000 years to reach star 1,000 light-years away at 10% of light speed. Mission duration equals entire age of civilization. This assumes civilization devotes resources to mission from very inception and maintains commitment across entire lifespan. In practice, interstellar exploration would be late-stage endeavor pursued only after millennia of prior development. Window of capability, period during which civilization possesses technology to launch interstellar missions but has not yet declined or transformed, might be remarkably narrow. Few centuries, perhaps few millennia at most. Multiply this constraint across galaxy. If intelligent civilizations are common, many may have risen and fallen already. Milky Way is roughly 13 billion years old. Stars have been forming and dying for most of that history. Planets with conditions suitable for life may have existed for 10 billion years or more. If civilizations arise, flourish, collapse within windows of few thousand to few million years, then galaxy at any given moment may contain civilizations at vastly different stages of development. Some just discovering fire, some building first telescopes, some launching first interstellar probes, some collapsing under weight of own complexity, some already gone, leaving behind nothing but cold ruins on forgotten worlds. Chances that two civilizations exist simultaneously within communication range of each other, both possessing interstellar capability, both directing efforts towards same target, are vanishingly small. Galaxy is vast, windows of capability are narrow, distances enforce isolation, and time, great eraser, ensures most civilizations will never overlap with nearest neighbors. Two candle flames burning in dark cathedral, each lasting only few seconds, separated by hundreds of feet. Probability both flames burn at same moment and light from one reaches other before it flickers out is almost zero. Not because candles are not real, but because cathedral is too large and flames are too brief. Entropy deserves special attention because it represents ultimate constraint no technology can overcome. Second law of thermodynamics states, total entropy of closed system always increases over time. Order degrades into disorder. Energy disperses from concentrated to diffuse. Complex structures break down into simpler components. This law governs every physical process in universe, without exception. No machine operates at perfect efficiency. No structure maintains itself indefinitely. No system resists entropy forever. For interstellar travel, entropy means every component of spacecraft degrades over time. Seals crack, circuits corrode, bearings wear, fuel decays. Biological systems accumulate damage. Even most advanced materials known to physics are subject to atomic-level degradation over sufficient timescales. Radiation damage displaces atoms from crystal lattices. Thermal cycling stresses molecular bonds. Micrometeorite impacts erode surfaces. Interstellar void is not gentle environment, preserving travelers in amber. It is slow-motion disassembly line, taking apart everything passing through it, atom by atom, year by year, millennium by millennium. Generation ship travelling for 10,000 years must fight entropy for 10,000 years. Every repair consumes resources. Every replacement part must be manufactured from onboard materials which are finite. Every system failing must be fixed before failure cascades into dependent systems. Over 10,000 years, even systems designed with enormous redundancy will eventually exhaust reserves. Mathematics of reliability engineering make this clear. System with 99.9% annual survival probability, meaning 1 in 1,000 chance of catastrophic failure in any given year, has only roughly 0.005% chance of surviving 10,000 years without single failure. Functionally, zero. To achieve even 50% chance of surviving 10,000 years, annual failure probability must be less than 1 in 144,000. These are reliability levels no human technology has ever approached. And they must be maintained not for single system, but for thousands of interdependent systems operating simultaneously in most hostile environment known. Final proposed solution to interstellar travel problem is self-replicating probe, often called von Neumann probe, after mathematician John von Neumann, who first formalized concept of self-reproducing machines. Idea is compelling. Instead of sending crewed ships across void, civilizations send single robotic probe to nearest star. Upon arrival, probe uses local resources, asteroids, comets, planetary materials, to construct copies of itself. These copies travel to next nearest stars and repeat process. Each generation of probes spreads outward, doubling numbers with each replication cycle. Even at modest speeds, such wave of self-replicating probes could theoretically colonize entire galaxy in few million years. This concept is strongest argument for feasibility of interstellar exploration, and it still fails under scrutiny. Self-replication requires manufacturing capability of extraordinary sophistication. Probe must be able to mine raw materials in alien environments, refine those materials into usable components, assemble exact copies of itself, including every sensor, every processor, every propulsion element, every line of its own programming. This is not three-dimensional printing. This is autonomous molecular-scale manufacturing in environments probe was not specifically designed for. Every star system presents different resources, different compositions, different challenges. Probe designed to replicate using asteroids in one system may find entirely different asteroid compositions in next. Replication also introduces mutation. No copying process is perfect. Each generation of probes will contain small errors, deviations from original design. Over thousands of generations, these errors accumulate. Some probes will malfunction. Some will replicate incorrectly, producing defective offspring. Some will lose critical capabilities. Wave of probes spreading across galaxy becomes increasingly degraded with each generation, subject to same entropic decay afflicting every physical system. Natural selection might preserve functional probes and eliminate broken ones, but this assumes probes operate in environments where selection pressures are consistent, which they are not. Every star system is different. Every replication cycle introduces new variables. Probe swarm evolves in unpredictable directions, drifting further from original purpose with each generation. And even if self-replicating probes work perfectly, timescale remains prohibitive. At 1% of light speed, colonizing galaxy takes roughly 10 million years. At 10% of light speed, roughly 1 million years. These are timeframes dwarfing lifespan of any known civilization. Civilization launching first probe will not exist when wave reaches distant star systems. Probes become orphans, carrying instructions from dead culture, arriving at worlds their creators never knew existed, executing mission whose purpose evaporated millions of years before first copy reached destination. Galaxy might eventually be filled with probes, but those probes would be fossils, artifacts of extinct civilizations drifting through star systems with no one left to receive reports. Every path leads to same conclusion. Universe is not merely large, it is structured in way enforcing isolation. Speed of light creates absolute ceiling on travel and communication. Energy requirements for relativistic travel create floor no civilization can dig beneath. Passage of time erodes ships, crews, civilizations, purpose with equal indifference. Entropy guarantees every physical system degrades, and distances between stars ensure every journey is measured not in lifetimes of individuals, but in lifetimes of entire societies. This conclusion should not be mistaken for pessimism about alien life. Nothing in this analysis suggests intelligent life is rare or absent in cosmos. Universe may be saturated with civilizations. Every galaxy might harbor thousands of thinking species, each one building, discovering, wondering, looking upward at their own unfamiliar constellations. Argument presented here has never been that aliens do not exist. Argument is that universe is designed, if design is even right word for blind architecture of physical law, to keep its inhabitants apart. This realization carries weight difficult to express without slipping into philosophical territory. This analysis has deliberately avoided until now. But here, at end, philosophical dimension deserves its moment, because implication of everything we have explored is not merely technical. It is existential. If intelligent life is common, if civilizations arise regularly on worlds scattered across Milky Way, then most likely, state of galaxy at any given moment is one of profound and permanent isolation. Thousands of civilizations, each one burning briefly against dark, each one surrounded by distances it cannot cross, energies it cannot muster, timescales it cannot survive. Not because they are stupid, not because they lack ambition, but because universe is too large and too slow for its inhabitants to ever find each other. Silence of cosmos is not evidence we are alone. It is evidence cosmos is very, very large and very, very quiet. Not empty, not hostile, just indifferent. Universe does not prevent life from arising, it prevents life from meeting. It builds walls of light years between every inhabited world and enforces those walls with most fundamental laws of physics: speed of light, conservation of energy, arrow of entropy, passage of time. These are not barriers future science will casually dismantle. They are architecture of reality, and they apply to every mind that has ever looked up and wondered. Candle flames burn in cathedral, brief, beautiful, scattered across immensity, dwarfing them all. Each flame illuminates its own small circle and casts no light beyond it. Darkness between them is not empty, it is simply too vast for any flame to bridge. If intelligent life is common, universe may simply be too large and too slow for civilizations to ever meet. Barrier is not technology. Barrier is not intelligence. Barrier is not willpower or resources or imagination. Barrier is distance itself.